Hello everyone! What I'd like to do in this video is just do a ton of examples of using the fundamental theorem of algebra. So remember what the fundamental theorem of algebra says is that if I have an nth degree polynomial, then that polynomial will factor into n linear factors, which just that means that any polynomial of nth degree will have n roots if we count multiplicity, and some of those roots might be complex. Okay, so let's just do some examples. Okay, so once I write this example up on the board for every single one of these, I want you to pause the video, try it on your own, and then we'll do it together. Okay, first example. What we want to do is we want to try to find all the roots of the polynomial x cubed plus x squared plus x. So I want to find all its roots, and I want it to factor it into n linear factors, or this should factor into 3 linear factors. We should find 3 roots. Go ahead and pause the video, give it a shot. Okay, so first thing I'm going to notice here is that I have a common factor of x. So the first step, we'll factor out that x, and we'll be left with an x squared plus x plus 1. So what I've done here now is I've broken this polynomial up into a linear factor. You could really think of this x as maybe x minus 0 if you'd like. So 0 is the root of this polynomial. So I've factored this polynomial into what's called a linear factor. Now I have a quadratic factor. So when you're left with these quadratic factors, you're either going to try to factor them by hand, or you're going to need to find the roots using the quadratic formula. Okay, so notice if you try to factor this by hand, you'd be trying to find the factors of 1 that add to 1, but the factors of 1 and 1, or 1 and 1, or negative 1 and 1, and those add to 2, and negative 2, no combination will add to 1. We cannot factor this nicely without using the quadratic formula. So I need to figure out when is x squared plus x plus 1 equal to 0. So the quadratic formula, solutions to this will be negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay, my a is 1, my b is 1, and my c is 1. Okay, so the solutions will be a negative b, a negative 1, plus or minus the square root. I'm going to get my b squared, so I'll get a 1 squared minus 4. My a is 1, and my c is 1. All over 2a, all over 2 times 1. So what do I get? I'm going to get a negative 1 plus or minus. I'm going to get the square root. Looks like I have a 1 minus 4 all over 2. Or it looks like we have a negative 1 plus or minus the square root of a negative 3 over 2. Oh, it looks like that I'm actually going to get 2 complex roots for this polynomial. Let's bring this up over here. So we have an x is equal to, we get a negative 1. Remember, we can write the square root of negative 3, is we can write that as I times root 3 all over 2. Remember, we like to write complex numbers in the form a plus bi, so I'll go ahead and distribute the 2. So this is going to be the same thing as negative 1 over 2 plus or minus. Plus or minus, how about we write this as root 3 over 2i. So what I can see is that the real part of this complex number is negative 1/2. Now, I have 2. I have the plus version, and I have the negative version. Okay, so the real part of both of these numbers is negative 1/2, and the imaginary part for the first one is root 3 over 2, and the imaginary part is negative root 3 over 2 for the second one. So I've found all 3 roots. 2 of them are complex, and one of them is real. So let's write down the roots, and let's make a quick observation. Okay, so what we'll end up getting is we have our roots. We have x equals 0. We have x equals negative 1/2 plus root 3 over 2i. And we have x equals negative 1/2 minus root 3 over 2i. Okay, notice here that I had a complex root Know what else came along for the ride? Its conjugate. What's actually really neat here is if I have a polynomial, which has real coefficients, which means the numbers out front are real numbers and not complex numbers, so the coefficients are 1, 1, and 1 for this one. If a polynomial with real coefficients has complex roots, it will always, if it has one complex root, it'll always have at least another one, which will be its conjugate. This will always happen. And we'll see with these examples, whenever you factor a polynomial, you'll always get down to linear factors and quadratic factors. Now, sometimes these quadratic factors may have complex numbers as roots. So if they do have a complex number as a root, you'll usually figure that out through the quadratic equation. And you'll always get a complex number and its conjugate. Why? Well, look at the quadratic formula. The quadratic formula will always have the plus or minus in it. So I'll always get a plus the imaginary number and minus the imaginary number. If I get one complex root, I will always have its complex conjugate. So I want to write that down. If the polynomial p of x has real coefficients, let's clear some space to write this down. This is something to remember. Okay. I don't want to erase all of this because I want to finish factoring this. I want to finish factoring this polynomial. I'll leave the roots out. But note, a polynomial with real coefficients, or we're going to say if a polynomial with real coefficients has a plus bi as a root, where b is non-zero, then a minus bi will also be a root. Okay. So if I have one complex number as a root, its conjugate will tag along for the ride. Okay, so let's go back to that first polynomial we had here. I just want to write it in its factored form if I know its three roots. So the polynomial p of x was x cubed plus x squared plus x. How will this factor? Okay, we had x as a factor. Okay, this is one of the roots. So I'm going to write this in a bigger set of parentheses. So I'll get x minus this root, x minus negative 1/2 plus. Sorry, wish I had a little bit more board space. We're gonna need some more room. Okay, I'll write it right here. So this will factor to an x times an x minus a negative 1/2 plus root 3 over 2i. Okay. Times, I'll have the other factor, which will be an x minus a negative 1/2 minus root 3 over 2i. So this is how that polynomial will factor. So I'll have x minus this root. So if I inputted this root back in, I'll have this number minus itself. It'll zero it out. Or I'll have x minus this root. So if I plug this into here, they'll cancel each other out and I'll get 0. So this is how this factors. Now you'll often see what the book will do here is usually distribute in this minus sign. So you might see the answers in the book be distribute this minus sign. That'll make this a plus and this a minus. And that'll make this a plus and also this a plus. So this is how this polynomial will factor. Has 3 roots and it's factored into 3 linear factors. Okay, let's do another example. Okay. Another example. Let's say we have a polynomial p of x is equal to how about 4x to the fourth minus, or how about 9? How about 9x to the fourth minus 16? Go ahead and give this one a shot. Okay, so what I'm going to actually notice about this problem if I want to factor it, or at least what I'm noticing, is I'm noticing that this is actually going to be quadratic in form, but I should also see that this is a difference of squares pattern. Notice that I could rewrite this as, how about 3x squared squared minus 4 quantity squared. So recall when I have a difference of squares, if I have a difference of the squares, a squared minus b squared, that factors to a minus b times a plus b. So I have a difference of squares pattern here. So this polynomial, this one right here, this will factor to 3x squared minus 4 times a 3x squared plus a 4. So now what I've done is I've taken this 4th degree polynomial and I factored it actually into 1, 2. I factored in 2 quadratic factors. Okay, I should be able to break these down more. In this situation, since I have quadratics, what I'm actually going to do here is I'm going to just figure out when each of these are equal to 0. So let's look at each of these pieces here separately. Let's start with this one. Okay, so this one here, I want to know when is 3x squared minus 4 equal to 0. You could use the quadratic formula here with a equals 3, b equals 0, c equals negative 4, but we can actually solve this really easily without the quadratic formula. How about I add 4 to both sides, so I'll get 3x squared will be equal to positive 4. We're going to divide both sides by 3, so I'm going to get x squared is equal to 4/3, and now I'm going to square root both sides. So I'm going to get x is equal to the plus or minus square root of 4/3. And I'm going to clean this up a little bit. So this will be x will equal to the plus or minus the square root of 4. The square root of 4 is 2. All over the square root of 3. Okay, now oftentimes it's going to be nice for us to do, it's going to be nice for us to rationalize the denominator. This is a common thing to do. So I'm going to multiply top and bottom by root 3 over root 3. This is the first best trick in the math book, cleverly multiplying by 1. So plus or minus 2 root 3 over 3. So I have roots so far. I have x would be equal to 2 root 3 over 3, and I have another one, x would be equal to negative 2 root 3 over 3. Okay, so I have 2 of my roots. Okay, let's figure out the roots from the second factor. Okay, this is almost going to be the same exact problem, except now, when I figure out when this is 0, I'm going to subtract 4 from both sides. So I'm going to get a 3x squared is going to be equal to negative 4, or I'll get x squared is equal to negative 4 over 3 when I divide both sides by 3. Now I'm going to square root both sides, so x will be equal to the plus or minus square root of negative 4 over 3. Now we can kind of pause here for a second. Notice I really have the same result here. It's just that over here I have a negative 4/3 and here I have a positive 4/3. So I'm going to get the same exact answer when I clean this up, except I'll just have an I out front. So x will be equal to plus or minus the square root, or sorry, 2 root 3 over 3 times I. So I have my other 2 roots. I also have 2 root 3 over 3 I, and I have x which is equal to negative 2 root 3 over 3i. Notice that when I had one complex number, I also got its conjugate. Okay, now let's talk about how this polynomial should factor, and we need to be a little bit careful when we set up the factoring for this. Okay. So what I have here, so basically what we need to do now is one of those polynomial building exercises. Okay, I have a polynomial. It has degree 4. It has these as its roots. But what is the leading coefficient of this polynomial? The leading coefficient of this polynomial is 9. And we'll want to keep that in our minds. So let's factor this. So this will be factor 2. Well, if this is a root, it'll have x minus 2 root 3 over 3. Let's actually scoot this over. We'll have an x minus 2 root 3 over 3 as a root. I'll also get x plus 2 root 3 over 3 as a root. Okay. I'll also have x minus 2 root 3 over 3i. And I'm also going to get x plus 2 root 3 over 3i. Okay. So let's be a little bit careful with how this polynomial here factors. Okay, what we should notice here is that when I multiply this polynomial out, or if I look at what the leading term of this polynomial is, I have an x times an x times an x times an x. The leading term of this polynomial is actually x to the 4th. This is actually x to the 4th. But the problem is, this is the leading coefficient of this polynomial is 9. So how do I make this polynomial have, right now it has a leading coefficient of 1, I want it to have a leading coefficient of 9. I can scale this polynomial by whatever I want. And so what I'm going to do is I'm going to scale this polynomial by 9. I'm going to scale this polynomial by 9. So now it has a leading coefficient of 9 times x to the 4th. And this is the answer. This is that polynomial. And this is its factored form. Okay, we got to be a little bit careful sometimes if we're just looking at our roots and we're trying to build the polynomial by thinking about its factors, we need to go back and make sure that we have the correct leading coefficient. So this is our answer. Okay. Let's do another example. Okay. Let's try this polynomial here. Let's try p of x is equal to, how about x cubed minus 4x squared plus 6x minus 4. Okay. Let's try to factor this polynomial here. Go ahead and pause the video and give it a shot. Okay. So what we're going to do here is, I see a polynomial that has 4 terms. I'm going to just check if factoring by grouping is going to work. So let's see if I group the first 2 terms and the second 2 terms. Okay. I can factor out an x out of this set of parentheses. So I'll be left with an x squared. Actually, I can factor out an x squared out of here. So I'll be left with an x minus 4. But the only thing I can factor out of these 2 terms here, I believe, is what, a 2? And I'll be left with a 3x minus 2. Unfortunately, the problem we have here is that these 2 terms here don't match. So I don't know if factoring by grouping here is going to work, unfortunately. Factoring by grouping will not work here. Okay, so what are we going to do? What we're going to do here is, the only other option we really have is to use synthetic division. Okay, so we have x cubed minus 4x squared plus 6x minus 4. We're going to use synthetic division, so the rational roots theorem says our candidates for possible roots will be plus or minus 1, plus or minus 2, and plus or minus 4. Okay, so let's just start checking them. Okay, so 1, negative 4, 6, and negative 4. Let's put a 1 here. Okay, we'll check if 1 is a root. So 1 times 1 is 1. We'll get negative 3. Here I'll get a negative 3. Here I'll get a 3. Here I'll get a 3. I get out a negative 1. Bummer. Okay, let's try negative 1. Let's try negative 1. Okay, 1. Here I'll get a negative 1, negative 5. I'll get a positive 5. I can see this isn't going to work. I get 11. I'll get negative 11. Bummer. Bummer. It's not going to get, I'm not going to get a remainder of 0. Okay, let's try 2. Let's try 2. Okay. 1. 2 times 2 is 2. I'm going to get what? Negative 2. I'll get negative 4. Here I'll get what? Positive 2. 2 times 2, yes! 2 times 2 is 4, yes! I found one of its roots. 2 is a root of this polynomial. I now know that it'll factor. 2 looks like x minus 2 times x squared minus 2x plus 2. So I was able to factor this polynomial into a linear factor and a quadratic factor. Okay, now we just need to factor, or we need to figure out the roots of this quadratic factor. Okay, maybe we can try to factor it by hand. You need to think of the factors of 2 that add to negative 2. The only options are 1 and 2, but neither of those combinations with pluses or minuses will add to negative 2. So I need to use the quadratic equation here to figure out the other roots. So here we will have, trying to figure out when x squared minus 2x plus 2 is equal to 0. Using the quadratic formula, we'll get a negative b, so a negative negative 2 plus or minus the square root b squared. I'll get a negative 2 squared minus 4. My a is 1 and my c is 2. My c is 2. All over 2 times a, my a is 1. Okay, so let's see what we get here. So we're going to get a 2 plus or minus. Looks like we're going to get the square root. What is that? It's going to be 4. 4 minus 8. 4 minus 8 all over 2. So it looks like we're going to get a 2 plus or minus the square root of negative 4 all over 2. Okay, I'm going to bring this over here. Sorry about that shadow. Okay. So what we're going to get is we're going to get, I need more room in here. I need more room in here. Okay, so we're going to get a 2 plus or minus negative root, the square root of negative 4 is going to be, I hope you believe, 2i divided by 2. You could distribute this 2 to each piece, so my roots are going to be 1 plus or minus 1. That's right, 1 plus or minus I. So I have a third degree polynomial. I got 3 roots. The roots are x equals 2, x equals 1 plus I, and no surprise, its conjugate tagged along for the ride. Okay, so let's factor this. So this polynomial will factor to an x minus 2. Okay, one of its roots is a 1 plus I, so I'll have an x minus a 1 plus I. And I'll have an x minus a 1 minus I. I'm totally fine if you leave your answer like this, but it's very common for the book to distribute in these minus signs. So I'll write this as x minus 2, and an x minus 1 minus I, and an x minus 1 plus I. So this polynomial factors into 3 linear factors. It has 3 roots. 2 of them are complex, and the complex ones have their complex conjugates to hang around. Okay, beautiful. So I guess kind of a question you might have is, well, what about graphing these? What would a loose sketch of this graph look like? Because I'm not getting any real zeros from this piece, well, let me just give you kind of a quick sketch of what it's going to look like. We're only going to really record visually the real roots. So if I were to graph this, I know this is how the polynomial factors, but our same factoring skills, or our same graphing skills is going to apply. It's going to have an end behavior of a cubic. It'll have the end behavior of a cubic. Its real zero is 2. Okay. It has a y-intercept. It has a y-intercept at what, negative 4. Let's move the 2 over. Let's move the 2 here. Here's a negative 4. So what this polynomial is going to do is it's going to have an end behavior down here, and it's just going to cross through. So I'm trying to graph. It'll probably look something like this. It's going to cross through these. It'll cross through 2 because it has a multiplicity of 1, but it still has that end behavior. But now when I graph it, I'm going to record on the graph the real root. So this is a rough sketch of what that polynomial here would look like. I have its end behavior. I know where it's going to hit the y-axis. I know where it's going to hit the real axis. I know what's going to cross through that real zero. Okay, let's do another example. Okay, let's try this one. Let's try p of x. P of x is equal to, how about a 3x to the 5th plus 24x cubed plus 48x. Okay. Go ahead and pause the video. Go ahead and pause the video and try to find the roots of this polynomial. And write it as, and use the fundamental theorem to write this as the product of linear factors. Okay, let's try it together. So what we're going to first notice here is I can factor out a 3 and an x. I can factor out a 3 and an x. So this polynomial is going to be a 3x. And what am I going to be left with? Well, I'm going to be left with a, looks like an x to the 4th plus 8x squared plus, how many times does 3 go into 48? 3 goes into 40, I think 16 times. So we'll write times 16. Okay. Okay, so I've been able to factor out the 3x. Now I'm going to look at this, this 4th degree polynomial I have left. And the big observation here is I don't need to use synthetic division. Again, you could use synthetic division if you wanted to. You could use plus or minus 1 and plus or minus 2 and plus or minus 4, plus or minus 8, plus or minus 16. Or we can notice that this is quadratic in form. This is quadratic in form. Okay, so let's kind of do a little aside here. A little aside, as we're going to try to figure out, we're going to try to factor x to the 4th plus 8x squared plus 16. We should notice that this is the same thing as x squared squared plus 8 times x squared plus 16. If you'd like, I'm going to make a substitution. We're going to let y equals x squared. Again, you don't have to do this step if you don't want to. I like it because I just think it makes the problem visually appealing. So this is the same thing as y squared plus 8y plus 16. So now I'm going to try to factor this. Okay, so I'm going to get a y and a y. I need factors of 16 that add to 8. Factors of 16 that add to 8, so 4. So 4 times 4 equals 16. They add to 8. And I think that we're pretty much we're pretty much done here. So this is the same thing. Well, not quite done. Y plus 4 quantity squared. So this is the same thing as x squared plus 4, x squared plus 4 squared. Okay, so let's go back and write that up here. I'm going to erase a little bit of this. So what we just realized is this factors to a 3x times, how about I write this as, instead of writing it as a square, how about I write this as x squared plus 4 times an extra x squared plus 4. I'm going to go ahead and erase this here. Okay, so now I've basically broken down this polynomial to the product of a linear factor and 2 quadratic factors. Okay, so what I want to do is, again, you could use the quadratic formula here to figure out what the roots of this are going to be, but I'm just going to go ahead and figure out when x squared plus 4 equals 0. If I subtract 4 from both sides, and I take the square root, I'll get plus or minus the square root of negative 4, so x will be equal to plus or minus what? 2i. Okay, so this polynomial is going to factor to 3x times, okay, well, each of these, this has a root of 2i and negative 2i. This is the same thing. It will also have a root of 2i and negative 2i. So I do have 5 zeros if I count multiplicity. One of my zeros, or one of my roots is x equals 0. Okay, this will have a multiplicity of 1. I'm going to get x equals 2i will be a root, but I'm going to get one of the 2i's from here and one of the 2i's from here. This will have a multiplicity of 2, and I'll also have x equals negative 2i, and that'll also have a multiplicity of 2. So it does have 5 roots if I count multiplicity. Okay, so let's write this in its factored form. Okay, I'm going to go ahead and erase what I have here. Okay. So this will factor to, I get a 3 times an x, so 3 times an x. This will have an x minus a 2i. And I'm going to get an x plus a 2i. But I'm going to get 2 copies of these. So if you want, that's me factoring this piece. If you want me to write an extra x minus 2i and an extra x plus 2i. Notice this polynomial factored into the product of 5 linear factors. But we could write this as 3x times x minus 2i squared times x plus 2i squared. And that's how this polynomial will factor. Okay? How fun is this? Okay, let's do another example. Okay. Ooh, let's try this one. Okay, I'm going to go ahead and erase the board. Okay, maybe we'll do 2 more. Okay, so let's say I have the polynomial. Let's say I have the polynomial p of x is equal to, how about x cubed minus 27? Okay. Go ahead and pause the video and try this problem out on your own. Okay, so here's my tip on this type of problem. Some of you may remember a difference of cubes formula. This is x cubed, and this 27 is 3 cubed. You could try to remember that difference of cube pattern. There's also a sum of cubes factoring pattern. To tell you honestly, I don't remember them. I've never remembered them. I've tried to commit them to memory. It's just never worked for me. So what am I going to do to factor this one if I don't remember the difference of cubes formula? Well, all I can really do here is synthetic division. And notice here, if I can find one of the roots, I can break this down. And so what I'd actually like to comment here is that I can easily find one of these roots without making even a huge list of them. For example, I can easily solve when x cubed minus 27 is equal to 0. That's when x cubed will be equal to 27. So x will be equal to the cubed root of 27. Remember, when you do cubed roots, you don't do pluses or minuses. You only do the plus or minus with even roots. Okay. So the cube root of 27, I believe, is 3. So what I know is I know 3 is root. We can check that. And if you plug in 3, 3 cubed is 27. 27 minus 27 is 0. I know one of the roots. So right off the bat, we know that x equals 3 is a root. That's like that little bird in section, what was it? Was the polynomial division one. At the end of 3.3, it's like that little bird whispered to us, x equals 3 is a root. X equals 3 is a root. So now we can use synthetic division to break this down. That's what I'm going to do. So we know x equals 3 is a root. So we know that x minus 3 is a factor. Okay, so let's break this down. So when I set up synthetic division bar here, I need to remember to record the zeros. So I have a 1 in front of the x cubed, I have a 0x squared, I have a 0x, and I'll have a minus a 27. Constant term, x squared term, x cubed term. Okay, and now we'll do synthetic division. Let's break this down. So I'll drop down the 1. 3 times 1 is 3. 3 plus 0 is 3. 3 times 3 is 9. 3 plus 0 is 9. 3 times 3 is 27, and ha! We get a remainder of 0. Beautiful. This is fun. Okay, so let's factor this polynomial. I know that x minus 3 is a factor, and the other factor would be an x squared plus a 3x plus a 9. It's fun. I love just breaking these down. Okay, now what am I going to do? I'm going to try to figure out the roots of this quadratic. Okay, if you try to factor it by hand, unfortunately, I don't think it's going to work out very nice. You try to find the factors of 9, so what, 1 and 9 and 3 that add to 3. None of those combinations will work, so we'll go just use the quadratic equation here, quadratic formula. We want to know when is x squared plus 3x plus 9 equal to 0. We'll use the quadratic formula, so I'm going to get a negative b, negative 3, plus or minus the square root of b squared, so 3 squared minus 4. My a is 1, my c is 9, all over 2a, my a is 1, so 2 times 1. So we'll get out a negative 3 plus or minus. What are we going to get here? What are we going to get? We're going to get, what is that? That's a 9, 3 squared, that's a 9 minus 4 times 9, what is 36? What is that, negative, what is that going to be, negative 27? Okay, so this will be the square root of negative 27 all over 2. So we can list all our roots here. Okay, one of our roots will be x equals 3. Okay, I could rewrite this so I don't have a negative under the square root. This is, how about we write this as negative 3 over 2, negative 3 over 2, and this would be plus or minus, that's going to be the square root of 27 times I, all over 2. Okay. If you want, we could break down 27 if we want to clean up this square root. So notice that 27 is the same thing as what the square root of 9 times 3. So this is the same thing as 3 root 3. So if you wanted to, we could write this as negative 3 over 2 plus or minus. This will be 3 root 3 over 2 times I. So we have our roots. We have 3 as a root. We have negative 3 over 2 plus the square root of 27 over 2i. We also get negative 3 over 2 minus the square root of 27 over 2i. So if I had this is a complex root. Notice its conjugate came along for the ride. Okay, let's factor this. We found the 3 roots. So this will factor to x minus 3. Okay, then we're going to get an x minus a negative 3 halves plus, I'm in front of the board, 27 over 2i. And the other factor is I'm going to get an x minus a negative 3 halves minus root 27 over 2i. Okay, I'm fine with you leaving your answer like this, but it's very common that the book will distribute in this minus sign. So this will be a x minus 3 times, how about an x? They'll write a plus. They'll write plus a 3 halves minus the square root of 27 over 2i, and then an x that'll be a plus a 3 halves plus the square root of 27 over 2i. So I've factored this polynomial into the product of 3 linear factors. I have a complex root, and its complex conjugate came along for the ride. Okay. Let's do one more. Let's do a super juicy example. This will be the last example we'll do. Let's do a 6th degree. This one will be spicy, but it'll be fun. Okay, last example. Let's say. Well, let's do one real quick one. Let's do a real quick one and then a super hard one. Okay. So, let's say p of x is equal to x cubed minus 2x squared plus 4x minus 8. Go ahead and give this one here a shot. Okay? So what I'm going to notice here, is, again, I'm not going to try to jump straight to synthetic division. What I'm going to notice here is I have 4 terms. So I'm going to try to use factoring by grouping. So let's group the first 2 terms and the second 2 terms. Let's see if it'll work. So I think I can factor out, looks like an x squared, and I'll be left with an x minus 2 plus. I can factor out a 4, and I'll be left with an x minus 2. Yes! Yes! Look! They have a common factor of x minus 2. Factoring by grouping here will work. Let's factor out the x minus 2. So I'll factor out the x minus 2, and then I'll be left with x squared plus 4. Okay, now I just need to figure out when x squared plus 4 is equal to 0. That's when x squared will be equal to negative 4. Or that's when x will be equal to the plus or minus square root of negative 4. Or this is when x will equal to the plus or minus 2i. So we have our three roots. We have x equals 2, we have x equals 2i, and we have x equals negative 2i. Let's go ahead and factor. So this will factor 2. This will factor 2, x minus 2, x minus 2, x minus 2i, and x plus 2i. And there we go. It's great. I didn't have to use synthetic division here. With some of these problems, just sticking to our factoring skills, we'll get through these problems a lot quicker. Okay. So let's do a super spicy example. Okay, so let's say we have a polynomial, p of x. Let's say it's equal to x to the 6th minus 7x cubed minus 8. Oh my goodness, I am expecting 6 roots for this problem. Okay, pause the video, give this one a shot. Okay, here we go. So the first thing I'm going to notice with this problem, before even, you could go ahead and you could jump straight to synthetic division if you wanted to, but the big thing I'm going to notice here, maybe using synthetic division, maybe it will be faster for this problem, but what I'm really noticing here is that this is a difference of squares pattern. Notice that this is equivalent to x cubed squared minus a 7x cubed minus 8. So let's go ahead and let y equal x cubed. So this is the same thing as y squared minus 7y minus 8. Okay, so let's see how this will factor. This will factor to, let's see, I need factors of negative 8 that add to 7, so the only possibility will be an 8 and a 1. They have to add to a negative, so the bigger of the numbers has to be negative. So putting all our pieces back, what we have here is we'll now have that x cubed, we'll have an x cubed minus 8 times an x cubed plus 1. Beautiful. We're going to need some board space here. I'm going to erase a little bit of this and kind of write this result up here. Okay, so we just realized that this 6th-degree polynomial can be broken down to x cubed minus 8 times x cubed plus 1. Okay. And now what I have is I really have two separate problems I need to tackle. Okay, I need to factor an x cubed minus 8, and I also need to break down an x cubed plus 1. I need to break both of these down. Okay. Okay, so for each of these, again, you could start using synthetic division. That's probably what I'm going to actually do for these. If you remember a difference of cube pattern, you can use those here, or a sum of cubes pattern, you can use that. Again, I forget those. But notice here, I can actually quickly see one of the roots. Notice here, if you want to figure out when this is equal to 0, that's when x cubed is equal to 8. And if I take the cube root of both sides, the cube root of 8 is equal to 2. So I know that 2 is a root. Similarly over here, if I want to know when x cubed is equal to negative 1, I want to figure out when this is 0. That's when x will be equal to the cube root of negative 1. So what number do I multiply by itself 3 times to get out negative 1? I hope you believe negative 1. Negative 1 times negative 1 is positive 1, times an extra negative 1 is a negative 1. So this will be equal to negative 1. So what we know, I'm going to erase a little bit of this. We know from here that x equals 2 is a root. Similarly here, we know that x equals 1, negative 1, is a root. Okay, so let's take advantage of this. and use synthetic division to break each one of these down. Okay, so for this one, we'll have a 2, and I'm going to write a 1, a 0, and a negative 8. Okay, let's break this down. So 1, 2, 2, 2, 2. 2 is a, wait, hold on, what's going on here? So bring x cubed, x squared, x, so drop down the 1, 2, add these 2. Oh, 2 times 2 is 4. 2 times 2 is 4. 4 plus 0 is 4. 2 times 4 is 8. So I get out 0 here. I knew something was wrong because I had to get a remainder of 0 since 2 is a root. Okay. So what I have here is this polynomial. This one will factor to x minus 2 times a x squared minus 2x, plus 2x plus 4. That's how this polynomial here will factor. Okay. We'll do the same thing. I kind of do both of these at the same time. We'll do the same thing with this one. So I know negative 1 is a root, so let's break it down. So a 1, a 0, and a 1. Okay. Drop down the 1. Negative 1 times 1 is negative 1. Negative 1, I'll get a positive 1 here, a 1. A negative 1 times a 1, I get a negative 1. I'll add these together, I'll get out 0. Okay. So we know that this polynomial here will factor to an x plus 1, because negative 1 is a root, times an x squared minus x plus 1. Okay. So I've broken these down. Okay, so now what I need to do is I just need to figure out the roots of these two quadratics, and I'm going to use the quadratic equation. I don't think I can factor any of these. Well, let's see. Can I factor any of these? I need the factors of, let's make sure I didn't make any mistakes. Let's make sure I didn't make any mistakes. Yeah, I think we're okay. The factors of 4 that add to 2, I don't think there are any. So 4 and 1, 4 times 1, and what? 4 and 1, 2 and 2, neither of those combinations will add to 2. So I got to use the quadratic equation. So when is x squared plus 2x plus 4 equals 0? I'll get a negative b plus or minus the square root. I'll get a b squared minus a 4. My a is 1, my c is 4. All over 2 times a, all over 2 times 1. So we'll get a negative 2 plus or minus. We'll get the square root. We're going to get a 4, but a 4 minus 16 all over 2. Okay. So we're going to get a negative 2 plus or minus. Looks like we're going to get the square root. We're going to get the square root of 4 minus 16, what, negative 12? Negative 12 over 2. Okay. Let's clean this one up here a little bit. So what are we going to get? We're going to write this as a negative 2 plus or minus. You could think of 12 as 4 times 3. Well, first of all, I'll get the I for moving out the negative 1. So I'm going to get an I. And the square root of 12 is the square root of 4 times 3. The square root of 4 is 2, so this will be 2 root 3i all over 2. So I could write this as dividing the 2 in. I'll get a negative 1 plus or minus. The 2's will cancel out. Root 3i. Okay. So we figured out the roots of this piece. I'm going to erase a little bit of this here. Okay. Okay, so we know that from here, x equals 2 is a root. We have also x equals negative 1 plus root 3i is a root. Also, x equals negative 1 minus root 3i will be a root. Okay, we're going to do the same thing over here. Here we have that x equals negative 1 will be a root. Okay, I guess what we should do is, before I write all that down, we need to figure out when this is equal to 0, so we'll have to use the quadratic equation. So when is x squared minus x plus 1 equals 0? So I'm going to get a negative b. My b is negative 1, so negative 1 plus or minus the square root. I'm going to get a b squared, a negative 1 squared, a b squared minus 4. My a is 1, my c is 1, all over 2 times a, so a 2 times a 1. Okay, so we're going to get what? 1 times negative 1, we're going to get a 1 plus or minus. We're going to get 1 plus or minus the square root of, what is this? Going to be a 1 minus 4 all over 2. So we're going to get a 1 plus or minus, this is going to be the square root of negative 3 all over 2. Or what we'll end up getting, I'll write it over here. Is we're going to get a 1/2 plus or minus. I'm going to get a root 3 over 2I. So I'm distributing the 2, and I'm writing the square root of -3 as root 3I. Okay, so we have all our roots. Okay, for this one, we have that x equals -1 as a root. We have x equal to 1/2 plus the square root of 3/2 I as a root, and x equaling to 1/2 negative the square root of 3 over 2I. So we have 6 roots. We found them all. Beautiful. Little bit of work, but how fun is this? These are like little puzzles. These are like little puzzles. So, this is like doing Sudoku. So, in the morning, instead of, drinking coffee and doing Sudoku and doing crossword puzzles, wake up in the morning, drink a cup of coffee, and factor some polynomials. That's what we should do. Okay, so let's factor this thing. Let's factor this. So this will factor to in x minus 2. I'm also going to get a x minus this root, so I'm going to go ahead and flip all the signs, so it would be an x minus a -1, so I'll get a plus a 1 minus root 3I. I'll also get an x minus a -1, so plus a 1 plus a root 3I. Okay, I'm running out of room, so I'm going to kind of continue the multiplication over here. I'll get an x plus 1 as a factor. I'm also going to get x minus a 1/2 minus a root 3 over 2I. And then a x minus a 1/2, and then it'll be a plus root 3 over 2I. So there we have it. The 6-degree polynomial, it has 6 roots. It's factored into the product of 6 linear factors. It has 4 complex roots. And since this is a complex roots, notice that they're coming in conjugate pairs. So there you have it. I hope you enjoyed this lecture. We'll see you in the next one. Take care.